but the signal actually coming out of the photomultiplier tube across that resistor, so when the current comes across the resistor and make a voltage, that voltage is tiny. It is really small. I don't remember what it was, but it's really, really tiny, and it's quite noisy, actually. Obviously, turning the lights off helps. That's why I have this in a dark room. I took it out. I took the camera flash to take the pictures, but it's actually in a very dark room most of the time. So I was testing it on the bench with light. I had to turn the lights off. I did a decent job at sealing it up, but still not perfect. So it's very low level and very noisy. I ended up amplifying this thing by about 1,000 times to get a usable signal level out of this thing. So what I did to amplify it is I had 3 op-amp amplifiers. So I had a non-inverting amplifier, standard times 10, inverting amplifier, again standard times 10 inverting amplifier, and again another standard times 10 non-inverting amplifier. None of these were perfect times 10. I had some 9.1 and 9.9K resistors for these here, so I've done my best to match the values in the schematic, but they're not going to be perfect. I built this quite a while ago, but I'll do my best. But my point is that none of them are going to be perfect times 10. Amplifiers, the amplification is going to vary from 9 to probably 11 times, worst case scenario. Probably not that bad, but nominally we have about 1,000 times multiplication. And the reason I have 3 op amps is not only to, because this way I can invert it. Obviously you could invert it with 1,000 times op amp, but there's a reason I'm not using a 1,000 times inverting op amp. And that's because when you actually start getting amplifications that big, you start to get lots of noise introduced to your signal, and op amps typically don't function well at that high amplification. In fact, I'm just using a standard LM324 quad op amp. 3 of the op amps I just described, and one of them is for the comparator. The reason, and I don't even think an LM324 can actually have that high amplification. Plus, this way is much lower noise, and I can actually test the signal at the output of each one of the op amps to make sure it's working fine. So it's nice to debug that way, even though it does require more resistors. I think this is a better design because times 10 is a pretty typical level for an op amp. They're gonna function properly at that level. This way there's not extra noise introduced from 1,000 times. So this is actually a really good technique. I would say if you need anywhere over 30 times amplification, you should probably use this technique unless you have a specialized op amp for your task. But I didn't, so 3 op amps in an LM324 worked just fine. And the reason I have an inverting amplifier in the middle is because the spike, this obviously you don't need this. This could totally be a non-inverting amplifier, is because the spike output from the photomultiplier tube actually goes down, and I wanted the spike to be up. Obviously, it's not a huge deal, but I wanted it to be up for the comparator so I could compare it. Obviously, it doesn't make a difference. You could just as easily compare it to see if it was lower than what you wanted instead of higher. And so it wouldn't make much of a difference, but this is just the way I wanted to visualize it on my scope, so it's not really a big deal to make an inverting amplifier that's times 10. The reason the inverting amplifier is in the middle is because if you notice, the inverting amplifier has a 1K resistor in front of it. So obviously the photomultiplier tube resistor here, the 500K, where the current from the photomultiplier tube is converted to a voltage, is very high impedance. So sticking a low impedance node on that resistor would totally undermine any of the voltage that was actually being created by it. If you were to place a low impedance node, it would totally undermine the voltage signal because it would drop the resistance so low. So if you know your op-amp theory, you'll know that both the non-inverting and the inverting inputs, if there's nothing attached to them like this, will have an ideal impedance of infinity. Obviously, that's not possible in real life. However, it's very high, in the order of hundreds of megohms, probably in the gigohms range. So it's, again, like my multimeter, it's many, it's assuming it's at least a gigaohm, which is probably accurate. It's many orders of magnitude higher than the 500K, so I'd be totally fine. So that's why I have a non-inverting amplifier. However, you noticed in the inverting amplifier, the signal actually goes through a 1K resistor before it actually gets to the op-amp node. And that drops our impedance to 1K, which is way too low, much lower than the 500K. So this is put in the middle because the first non-inverting amplifier has such a high impedance that it doesn't matter. And the output of the first amplifier, all the current that's going to be drawn with the lower impedance, so all the impedance from the 1K resistor in the inverting amplifier and all the current that's going to draw is going to be buffered by the op-amp, if you will, and it's not going to influence the resistor. So the op-amp is going to sort of separate the 500K resistor from the inverting amplifier. And it's not going to draw too much current from the 100K, and it's not going to influence the impedance from the 100K because that all goes through the op-amp. That's the beauty of an op-amp. And then I just have another non-inverting amplifier to get the amplification that I want, which is about 1,000 times. And that puts the signal pretty close to being in the full range of negative 12 to 12 volts. So I have a negative 12 to 12 volt, actually negative 12.7 to 12.7 volt supply. And actually, the spikes that this thing makes, so remember the spikes go down coming from the resistor, and so I have an inverting amplifier, so now the spikes are going up, and the spikes actually get clipped because the LM324 has fairly poor rail-to-rail response. So if you were to take an LM324 and put it at 5 volts, the maximum it can give you on the output is around 3.9, which is very low. Okay, so it has pretty poor rail-to-rail response. So when an op-amp clips, it means that it's actually, the signal is higher than it can give you. So if you were to have a 5 volt supply, for instance, and you wanted it to give you 4.5 volts out, it would clip that signal down to 3.9, and that's called clipping. It's bad for when audio amplifiers do that. You can hear it. It sounds very poor, very bad. So the op-amps that I have, the final non-inverting amplifier actually clips the peaks to, I don't quite remember, but I can calculate the value. I'll put it on the screen. But it actually does clip the peaks. So they would, I may actually not need this much amplification, but it gives me a very nice signal, nice and clean, and it works fine. So why fix something that's not broken, you know? But it does actually clip the signal. There's a flat line when really the signal should look something like this. It looks like this. So, you know, I may actually have technically too high amplification, but this makes my job with the comparator much easier. So, before I get to the comparator, I actually send the signal from the output of the final non-inverting amplifier through a high-pass filter. And this is because on the signal, if you look, it looks something like this. Okay, there's many 60 hertz frequency from the light and lots of noise all over the signal. And if I was to not use this high pass filter, the actual peaks from the bottom of the trough, so wherever it hits the bottom of the trough in the 60 hertz, actually don't even make it up to the peak of the trough in the 60 hertz. So even if it was to spike at the bottom, it wouldn't even get to the top. And so you notice if we're to draw a voltage over time graph and draw a peak at the trough of the graph, you'll notice that if we can't have the comparator set to just find that peak, because it'll find the just to find the peak, because it'll also find the peak from the 60 hertz signal as well as the peak from the cosmic rays. So to try to get rid of all this low frequency, I have a high-pass filter which is composed of a 100 nanofarad cap and a 6,800 ohm resistor. So you notice these are both standard range. I just used the closest standard range components I could get, and really I just eyeballed the frequency, so I used some of those online calculators, eyeballed these values, and it gave me about 234 hertz cutoff frequency. So I figured that'd be adequate enough to cut off the 60 hertz frequency. And it does. It doesn't do a whole lot, but it definitely does enough so that the comparators can come in and do their job properly, which is actually where most of the filtering is done, is in the comparators. But this high-pass filter is very important because the comparators couldn't do their job, and it actually does remove quite a bit of noise. Obviously, there's quite a bit of high-frequency noise from background radiation, from radiation coming from me, extra light slipping in, you know, extra electromagnetic fields that are generated by the power supply and all that good stuff. So a lot of the high frequency noise still comes in, but it definitely lowers the value of the low frequency noise significantly, and that's very good. So that helps. So then the signal goes into a comparator, which is just the fourth op amp on the LM324. So the signal goes into the inverting input, and I actually have a voltage divider on the non-inverting output, or non-inverting input, sorry, and the output is going to go high whenever there's a cosmic ray. And I have the comparator voltage set to about 7.9 volts. So when the voltage on the non-inverting input goes above 7.9 volts, the output is going to go high, and so that's how I know there's a cosmic ray. And if it doesn't go above 7.9, it's going to drop the voltage down to ground. So actually, it's not going to drop it to ground, it's going to drop it to -12. So this way, this is where I'm accomplishing most of the filtering, because I've already gotten rid of the low frequency signals, but now I'm getting rid of any particles not only that are of a too low energy, because the higher the energy of the particle, the more voltage the spike will be. So I'm getting rid of particles below a specific energy, and I'm also getting rid of background radiation. So this is in fact another type of filter, and it gives me a nice clean spike on the output, just a real sharp, nice clean spike, which is what I want.